Topic number 4-5, difference of squares. The first question asks us to name some perfect squares. Then we need to think, what is a perfect square? Perfect squares are numbers that are the result, the product of two numbers being multiplied together, the same two numbers. So for instance, 1 is a perfect square because that can be written as 1 times 1. So we've got 1 times 1, the same number. So a number times itself is 1. So 1 is the perfect square of 1 squared. Now we've got 4, as that is 2 squared, or 2 times 2. 4 is a perfect square, 1 is a perfect square, 4 is a perfect square. Let's think of some other perfect squares. We've got 9, which is the result of 3 squared. We've got 16, which is the result of 4 squared. 25, which is the result of 5 squared. And you could go on, so forth, so on and so forth. You know, we would get to 36, then to 49, 64, 81, so on and so forth. 6, 7, 8, 9, 100. Now, we're going to use these perfect squares in combination with factoring today. So the question asks us to factor some perfect square binomials. Let's look at question number 1. It's a perfect square binomial. So if you notice, a squared can be written as a times a, 1 can be written as 1 times 1. But so far, we don't have a set way to work with this. So let's use our sums and products method. We've got a box over here, so we can use our sum to and multiplies to. Now let's think. There's no middle term in this case. We can go ahead and fill in our box. We've got the a squared and the negative 1. Remember that the multiplies together is the result of multiplying these two diagonals right here. So we've got a squared times negative 1 would make a negative a squared. We've got a negative a squared. Let's think. Now we don't have a middle term so far, but we can write it. We could write this as a squared plus 0a minus 1. A squared plus 0a minus 1. Now let's think. If I added a 0a, I didn't change the value because I added 0. I added nothing to this. So I just changed the way this equation looks. I've got the a squared plus the 0a minus 1. So in this case, our middle term is going to be this 0a. So I need to think of two expressions which I multiply out to get negative a squared that add up to 0a. Well, let's think. If I don't see a coefficient, I assume for it to be 1. So I've got the negative 1a squared. Factors of negative 1 are positive 1 and negative 1. So I'm going to have a 1 and a negative 1. And then I need them to add up to a, so they have to be like terms with a, so they're both going to be a. So I've got a positive 1a and a negative 1a. Positive 1 times negative 1 makes that negative 1. The a times the a makes the a squared. Now I've got 1a plus negative 1a. So I could do that as 1a minus 1a. That gets to 0a. So far so good. We've done our sums and products. Let's fill in our box. Now we've got the 1a, and then we've got the negative 1a. Well, let's think. A times a would give me a squared. So I already have that. A squared. Now what times a would give me negative 1a? Well, I would just have to multiply by negative 1. If I've got a times 1a, or rather, what do I multiply by a to get 1a? In this case, I just multiply by a positive 1. And if you notice, a positive 1 times a negative 1 makes a negative 1. So the correct factorization for a squared minus 1 would be a plus 1 times a minus 1. So far, so good. So we've got a squared minus 1 was factored out to a plus 1 times a minus 1. So go ahead and keep that in mind as we go on to number 2 and see if we'll be able to find any patterns. Now let's think. This time we've got a 9b squared minus 4. So I'm going to rewrite that as, we're going to write that as 9b squared plus 0b minus 4. I'm going to go ahead and fill in my box. So I've got the 9b squared and then the negative 4. Now I want to fill in my sums to and multiplies to. So I'm using my sums and products for this one. multiplies 2 is the result of multiplying this diagonal right here, so 9b squared times negative 4 would make a negative 36b squared. Now I need to think I've got my sums 2, which is 0b at our middle term, Now we've got negative 36b squared. So let's think. We need, since it's a negative product, one of them is going to be positive, one of them is going to be negative. They're both going to have b's. Now we just need to think of the coefficients. Now we need to think, they need to be the same number. We need to think of something. So remember back to our perfect squares. 36 is the result of 6 squared. So why don't we do a positive 6 and a negative 6? If you notice, 6b minus 6b would give me 0b. And if you multiply these out, we get the negative 36b squared that we need. So we'll fill in our box. We've got the 6b, the negative 6b. So far, so good. Now, we'll go ahead and work out. Let's think. Since we've been working with perfect squares, we'll want to use perfect squares for this. So 9 is a perfect square, which is 3 and 3. And then b squared would be b and b. Now let's think, what could I multiply by 3b to get negative 6b? Well, I've got the b already. Or, my mistake, I've already got the b, so I don't need to write that. I just need to think of a number. So I'll try negative 2. A negative 2 times a 3b. Negative 2 times 3, negative 6b, and then there's my b. 1 times 3b would give me 6b, and positive 2. Now look, we've got 3b times 3b, 9b squared. 3b times negative 2, negative 6b. 3b times positive 2 is 6b, and a positive 2 times a negative 2 gives me a negative 4. So the correct factorization of 9b squared minus 4 is 3b minus 2 times 3b plus 2. If you notice, 9b squared can be factored as 3b minus 2 times 3b plus 2. Now if you notice, we've got the a squared minus 1. That got factored into a plus 1 times a minus 1. 9b squared minus 4 got factored into 3b minus 2 and 3b plus 2. So it's asking us for a pattern. We need to think of a pattern we've seen. Now if you notice, if we think of a as a perfect square, a can be written as a times a. We've got the a and the a squared. And then we've got a 1. 1 is a perfect square as well. 1 is the result of 1 times 1. But notice that this is a negative 1. Our negative term, the negative 1, occurs as a plus 1 and a minus 1. Which makes sense because a positive 1 times a negative 1 would give us back our negative 1. We've got the a times the a, that makes the a squared. If we were to go ahead and use our distributive property, we would distribute this, well, we would end up with the same thing we ended up with our box. We've got the a squared, the a times the a, so there's the a times the a times the negative 1, so here's the a times the negative 1 gives me negative 1a, and the a times the positive 1, so I've got this a times this positive 1 gives me this 1a, and the positive 1 times the negative 1. These middle terms cancel out, so it gives us back our difference of perfect squares, our difference of squares. We've got a squared minus 1, factor into a plus 1 times a minus 1. Notice here, 9b squared. The square root of 9b squared could be thought of as 3b and 3b. So 3b times 3b gives me 9b squared. The square root of 4 could be worked as 2 and 2. I've got a negative 2 and a positive 2 in order to get my negative 4. And notice the middle terms cancel out again. So we've got a pattern. So far our pattern seems to be, and this works for any general difference of squares. We've got a squared minus b squared. Well, according to our pattern, we're going to open up two sets of parentheses, and that's what we're factoring in. A squared. A squared can be thought of as a times a. B squared can be thought of as b times b. Notice the negative term in this case is our b squared, so it shows up as a positive b and a negative b. Now let's make sure we've got a times a is the a squared. A times a. We've got a times b makes our negative AB. I write that as negative AB. And then I've got a positive B times A. Positive B times A can be rewritten as A times B. Since order of multiplication is commutative, it doesn't matter. We've got A squared minus AB plus AB. And then we've got a positive B times a negative B makes a negative B squared. Notice, we've got 0 pairs right here. And we ended up with our A squared minus our B squared. So this works. We can substitute anything for A. It's going to be a square, anything for B. And this will work out as a difference of squares. So for instance, if I gave you 9x squared minus, let's say, 64. Well, we'll open up our parentheses. And then let's think. For 9x squared, well, we've got a 3x and a 3x. Since the square root of 9 is 3, the square root of x squared is x. And then we need the square root of 64. That's going to show up as an 8 and an 8. Let's think. Since our 64 is our negative term, we're going to have a negative 8 and a positive 8. And this works out. We multiply these, we get our 9x squared. Since we're multiplying by the same values, except one is negative, the middle terms will cancel out, and then we've got the negative 8 times the positive 8 makes the negative 64. So we've got a pattern where we see the difference of two squares can be written as A plus B times A minus B, where A is any number, B is any number. So let's continue on. Now it asks us to factor these mentally. So for difference of squares, we no longer need to use the box and blocks method or the sums and products method, as long as it's the difference of two squares. So let's think. We've got x squared minus 9. So we'll open up a parentheses. We've got x squared can be written as x times x, since the square root of x squared is x. We've got x times x. Now 9, the square root of 9 is 3. We've got the 3 and the 3. We've got a negative 9. So we'll need a positive 3 and a negative 3. Just for the sake of checking for completeness, we'll check. We've got x times x is x squared. X times negative 3 makes a negative 3x. A positive 3x because we did positive 3 times x. And then we've got a positive 3 times a negative 3 makes the negative 9. These are 0 pairs, working with our algebra tile, so we've got x squared minus 9. We ended up with the same thing, so let's work with the next problem, which is d squared minus 121. So d squared, we can think of that as d times d. 121 is 11 squared, so 11 times 11. The 121 is our negative term, so we'll need a positive 11 and a negative 11. So now we've got d squared, and then negative 121. Again, if we were to distribute this out, we would see that our middle terms would make 0 pairs and that they would cancel out. So we've already got our correctly factored form. Let's work on number 5. Now we've got a 9h squared minus 144. So we'll open up a parentheses. Now let's think. 9h squared. So h squared is h times h. And 9, 3 times 3. So 3h times 3h, 9h squared. 144, 12. It's 12 and 12. The 144 is negative, so we need a positive 12 and a negative 12. Let's think. 3h times 3h, 9h squared, positive 12 times negative 12, 144. If we were to distribute out these middle terms, the 3h and the negative 12 and the positive 12 and the 3h, we would see that they would form 0 pairs, that they would reduce to 0, so we've got our original product. Now notice on number 6, we've got two variables. We've got two variables. We've got the k squared and the j squared. But our difference of square rule will still work on this. Let's think. We've got a 25k squared and a 64j. So we've got 25k. Let's think of that one first. This one's our positive term, so we've got the 25k. We've got the 5, which is the 25, and then the k. Then we need another 5k. This would give us our 25k squared. 64j, well 64 is 8, j squared j, and then another 8j. Since our negative 64j squared, since 64j squared is our negative term, we need a positive 8j and a negative 8j. 5k times 5k, 25k squared. And then we've got positive 8j times negative 8j makes the negative 64j squared. Looking good so far. If we were to go ahead and distribute out these outer terms, like the 5k, the negative 8j, and the 8j and the 5k, you would see that they would form a zero pair, and they would cancel out. So this is the correctly factored form of number 6. Number 7 asks us to do 16x squared minus 49y squared. So we'll open up the parentheses. Now we'll need, for 16x squared, well, 16 is 4 and x, and 4 and x. We've got 4 times 4 is 16, x times x, x squared. So far so good. 49, the square root of that is 7, the square root of y, so y squared is y. We've got 7y and 7y. Since this is our negative term, we need a positive 7y and a negative 7y. 4x times 4x, 16x squared, positive 7y times negative 7y is a negative 49y squared. This is our correctly factored form. For number 8, we've got 4z squared minus 9a squared. So we'll open up parentheses. Now let's think. For 4z squared, we've got a 2z and a 2z. 2 times 2 is 4, z times z is z squared. Then we'll need the 9a squared, which can be as 3a and 3a. 9a squared is our negative term, so we need a positive 3a and a negative 3a. So we can write 2z times 2z is 2z, 4z squared. Positive 3a times negative 3a makes the negative 9a squared. If you were to go ahead and distribute out your terms, you would see that we would get 4z squared minus 9a squared. They would form zero pairs. So this is our correct factorization. Now if you'll notice on number 9, we don't have a difference of squares, we have a sum of squares. Unfortunately, our rule doesn't work in this case. Now, we'll write both cases. Let's say if we wrote 2a plus 5b times 2a minus 5b. If we were to distribute this out, we would get 4a squared minus 10b plus 10b minus 25b squared. So we've got 2a times 2a makes the 4a squared. 2a times negative 5b makes the negative 10b. 5b times 2a makes the positive 10b, and then 5b times negative 5b makes the negative 25b squared. So yes, these form zero pairs, but notice that we ended up with 4a squared minus 25b squared, which is not the same problem we started off with. Unfortunately, this difference of squares rule that we derived doesn't work when it's a sum of squares. Now you could try checking for sums and products, but you'll see that that one doesn't work either. The best case scenario in this case would be to check for any greatest common factors. Well, A is only common to itself and B is only common to itself, so we've got no A or B in both of them. And 4 has factors of 2 and itself, but neither 2 nor 4 can go into 25, so there's nothing to factor out there. So this expression is as factored as it's going to get. So we can write this as a prime expression. Now I notice some people said, oh, mister, can't we use decimals and fractions to factor? Now we can, but we don't consider that a factor with using whole numbers. Now let's think of a prime number 7. 7 has factors of 1 and itself. Now someone could say, oh, but I could write 7 as 2 times 3.5. Yes, but see, this is not the factorization, the prime factorization, because it's not whole numbers. So same thing when we're working with factoring. At least for now, when we're just factoring, we're only concerned with getting whole numbers. So if you can't get a whole number factorization any further than you've already got, then we've got prime. Now let's think for number 10. This one includes fractions. So let's work. We'll need a c and a c, at least. We know that c times c would give us the c squared. And then we've got a 64d. Well, 8d and 8d. We can fill in our plus and minus, since this is our negative term. Now let's think. If we had 3 times 3 is equal to 9, which is 3 over 1, times 3 over 1 equals 9 over 1. Now let's check if the inverse is true. What if we do 1 over 3 times 1 over 3? Well, what does that give us? Well, we've got 1 times 1 is equal to 1. 3 times 3 is equal to 9. We've got 1 over 9, so we can fill this in with 1 over 3 and 1 over 3. So when we were working with fractions, for instance, if I gave you, let's say, 49 over 64, that can be rewritten as, well, the square root of 49 is 7, so we can say that's 7 times 7. And then the square root of 64 is 8, so we could say as 8 times 8. So if we were needing to use perfect squares, we could use 49, 64, or any combination. That covers our difference of squares. So remember, when we've got the difference of perfect squares, 16x squared minus 49, we break it up to fractions. Take the first term, take the square root of it, put it on both sides. Same thing for the second term, but the negative term is going to have a plus and a minus.